Good morning, class. Welcome to our science seminar today. We have another exciting math seminar, science seminar sequence today. We have with us Jonathan L. Mitchell from Austin, where we've had a number of other interesting guests of late. Dr. Mitchell has his doctorate in computation and applied mathematics from Southern Methodist University. He has his master's from Stephen F. Austin University, and also his bachelor's degree from Stephen F. Austin University, where he is teaching now as a math professor. But more so than that, Mr. Mitchell has a brother who is a LeTourneau alumni. So Jonathan Mitchell is not, a stranger to this campus. He knows a little bit about us, and that's kind of nice. He also has a number of kids who he likes to read books to. And let's see, what other exciting things he likes to do? Something about baseball in the box. What is it? Likes the study of epidemiological models. Heard of it here, Mr. Wesley? Yeah, that was his thing as well. Okay. He likes parasites. Oh man, this guy's interesting, isn't he? Bifurcation theory. Oh man. We don't need more division in our society, do we? All right. Anyway, he's going to tell us today about nonlinear oscillators. Let's give him a warm round.
All right. Thank you for a kind introduction. I'm not sure what to make of the "I like parasites" comment, but I'll move on from there. So thanks for coming. I'm humbled to be here at LeTourneau University in your science seminar. I'm hoping we can have a good time discussing some mathematics behind linear and nonlinear oscillators. Here's the basic outline. I'll tell you a little bit about the harmonic oscillator with some specific everyday examples that you may have even run into today, most likely. We'll derive the mass spring system, and we'll talk a little bit more about some nonlinear examples of oscillators and some methods that we can use or have been used in the past as how to approximate solutions, and we'll go from there. So, you've probably seen a guitar. The strings on a guitar are excellent examples of a harmonic oscillator. As the string vibrates, it can create all sorts of sounds. You can change the pitch and so forth based on where your finger is on those frets, but that is a good example, primarily because a harmonic oscillator has a restoring force, okay? So if you displace an object and there is an inherent restoring force pulling it back to a natural rest position, then that sort of creates this idea of oscillations. And for the guitar string, if you pull it to a certain position, you feel the tension in the string wanting to return it. Other examples, lasers, electromagnetic waves, are examples of oscillators. In this case, the oscillators don't really need a medium, right? As I'll leave our physics experts to discuss how that works, but it is an example of a wave. A coffee mug I find kind of funny because as we bump it or disturb it or perturb the coffee mug, you see it oscillate, right? Because of the weight of the coffee, if you bump it, it's going to maybe oscillate back and forth. There is a restoring force to return it to its rest position. So this is a fine example, especially as we try to keep that rest position and walk through the hallway from the break room. We need to keep the coffee mug from spilling over. Skyscrapers. Now, maybe you're thinking, I was with you for a while, but you're saying that a building oscillates? And precisely, yes, that's exactly what I'm saying. This is an example of a skyscraper. It is the Taipei 101 in Taiwan that was built rather recently. And if you were a tenant in the top of that building, you could very likely feel some sway to that building. And I can imagine that's quite unnerving to experience as you're thinking, oh my gosh, I'm hundreds of feet into the air. What's going on here? Is it an earthquake? No, that's just some wind, sir. some wind is pushing this building back and forth. So there's ways to deal with that, which I think are pretty interesting. In this particular case, for this building, there was a lot of headlines behind a tuned mass damper to try to decrease or to settle down these oscillations in the Taipei 101 building. And we might get a chance to talk a little bit about that. There's a really cool link I can kind of show y'all, perhaps if there's time at the end of the talk, as to how this works. We'll see if some of our nonlinear examples can touch on that. But the idea is you want to do something structural that diminishes this sway, the swaying that's going on. We need that to go away because all of our tenants are throwing up and becoming sick. Seasick, as it were, I suppose. So those are some everyday examples. And to build that case, I want to start with a mass spring system. We may have some students in here that have taken some Cal 1, some Cal 2, maybe differential equations. Anybody in differential equations? Anybody? Show of hands. A couple. I did see a few hands there. Okay, so you either have talked about the mass spring or you will soon. If not already, we're at November 9, right? So if you haven't yet, I guess you better hustle there on this course. But the idea here is Hooke's laws. The spring produces a spring force. As you displace the mass, there is a force on the mass that is negatively proportional to its displacement. The minus sign is just telling you the direction. If you pull it to the right, it wants to go to the left. If you pull it to the left, it wants to go to the right. And so based on x, the displacement, you'll get a spring force. You'll also get friction force if you allow for friction. That is proportional to the speed of the object. We're not going to put a huge distinction between static friction and kinetic friction. We'll just say friction. We'll say it's moving, and the speed that it's moving is going to produce this force, this friction force. It is also, but it's negatively correlated to the speed, because as it's moving one way, that friction force is fighting against it, the opposite direction of the speed of the velocity of the mass. And then we've got Newton's second law of motion. So we can put this stuff together and build a differential equation. The sum of the forces is mass times acceleration. Now my Cal 1 students, raise your hand if you've had Cal 1. Should be a lot of you, right? The first derivative of the position is what? Velocity. And the second derivative of position is? Acceleration. Oh my gosh. All right. You guys, right on task. So, and so out of this equation, we've got acceleration turns into the second derivative of x, and the first derivative, the velocity is the first derivative. I can divide by the mass, assuming it's a non-zero mass, which shouldn't be too bad to assume. And then voila, we've got our equation for a harmonic oscillator that governs the position of this mass spring. Dependent variable is x, independent variable is time, and delta is our damping coefficient, which governs how much friction there is, and then beta is the spring coefficient. So you might imagine a shock absorber on a car is an example of a spring, has a very strong spring, so beta would be very large for that. But a weak spring, like say Slinky, not a very strong spring, right? So that'd be a very small beta. So we can quantify some of these parameters based on what sort of situation we're at. And I'll try to keep this throughout the talk. Even when I get to nonlinear oscillators, I'll keep x my dependent variable and time my independent variable so that there's some consistency between equations as we move along. The good news is we, mathematicians and undergraduates, can say quite a bit about this equation. We can solve it. We can look at simulations of it. So let's look first at a mass spring system that is undamped. And you'll see that if there's no friction, maybe you can imagine it being on ice, if that helps. But if there's no friction, then this thing just goes back and forth, back and forth. You get sines and cosines. In reality, there typically is some friction. So this isn't the realistic approach. This is sort of a mathematically ideal system, right? That maybe we could think of. But the truth is, it's more likely this scenario where there's a little bit of friction and you'll see your mass spring system settle down. So maybe it's oscillating back and forth, but what was kinetic and potential energy exchanging perfectly is now being lost to heat energy, and friction is taking that energy and converting it to other forms. But it settles down, right? We look at this and say, okay, that's what I would expect to see for a typical mass spring system. But that's not the only case. There's also what we call overdamped system, which there is way too much friction. So imagine putting a mass spring system on maybe a surface like rubber or sandpaper. Okay, it's not going to oscillate a lot. And in this scenario, you see something like this. Well, that's not very exciting. You might say it's not even oscillating at all, right? There's too much friction, okay? It is over-damped. And so once it gets basically at zero, it stays at zero for the rest of time. So not terribly interesting. Those are your basic three possibilities for the harmonic oscillator that you can encounter. And the good news there is we know exactly those solutions in those scenarios. We can predict if you've got delta of 3 and beta of 2, I can produce the solution. And it's an overdamped case over here. If delta is small number and beta is much larger, then I can get that solution as well. We get decaying oscillations with the exponentially decaying amplitude and sines and cosines basically for the back and forth. And even in the no damping case, if it's undamped, we get sines and cosines. We can attain these solutions guess and check. We have things called the characteristic equation where we can solve for the eigenvalues. Anybody taking linear algebra? All right, you've heard the word eigenvalues. Big idea in mathematics and physics and other places. So turns out these values, -2 in the top left. I wonder if can I zoom in there? Yeah, the overdamped case. -2 and -1 are the eigenvalues for that system, turns out. Over here, eigenvalues are complex with the real and imaginary part. And then over here, the eigenvalues are complex or purely imaginary in this case. But I'm not, unfortunately, going to get to go into complex numbers. I wish I could. We could talk about Euler's formula, and that would be a lot of fun. I will say a takeaway from here is that solutions to linear differential equations are exponentials. Okay? E to the x. It's one of those scary functions at first until you take Cal 1 and learn that the derivative of e to the x is
e to the x.
One who's yelling. I love it. So, yeah, that makes e to the x, in my opinion, the most fundamental function in all of applied mathematics because it's its own derivative, which is wonderful. So you see the exponential functions show up lots of places, including solutions to all linear equations. Now, what happens if I take this mass spring system and I start doing things to it? So, for example, forcing or taking an oscillator and driving it with some sort of external force, something that's acting on the mass spring system. Maybe we imagine the skyscraper and it sort of has some sort of oscillatory behavior. We want it to settle down, so maybe it's the underdamped case. Would be great. But what if there's like a wind that's blowing? Well, is that going to affect the way it oscillates? Absolutely. It could cause some oscillations, in fact. So that forcing is usually described by a function of time on the right-hand side. Instead of your homogeneous case, which is nice here, you now have the oscillator with a function over here on the right. I like to tell my students that what's on the left is how the system would operate if left on its own. And then what's on the right, the non-homogeneous term, is something external to it that's acting on it. And they sort of interact, right? They interact with each other. And there's quite a few examples of forcing that we could talk about. I won't show them all. Let me show a couple of them. I mentioned the building with like a gust of wind. What might that look like if we had a mass spring system with like a gust of wind acting on it? That's what I want to get to. Let's see if this, there we go. All right, so what we just saw was there was this gust of wind. Did y'all see the blue mark arrows to the right, the blue vectors? It was pushing the spring away from its natural position. Now it's still sort of oscillated, but that gust of wind was sort of keeping it away from that green line, green dotted line. Maybe watch that again, and you'll see that happen again. But then eventually this gust of wind goes away, and oscillations sort of settle down to where you would expect them to. But it is affecting the system, and you do have something that's not quite the same as what we just saw. I don't want to get too deeply into it, but you see this phrase up here, phase plane. What that's doing is comparing the position of the spring left to right with the speed of the spring up and down. So if you put those together, then the undamped case where you get just sines and cosines would end up being perfect circles, right? Because it just kind of keeps going. So you're doing it circle. You might think about sines and cosines put together in that sense. But if there's forcing acting on it, well, then the spring does all sorts of crazy things. Because the vector field itself is changing. It's literally changing in time, which is why you saw those arrows move. That was the gust of wind. There's other sorts of forcing that are a little more interesting than just the gust of wind. Maybe we have an example where you have periodic forcing. So now the forcing is like a sine or a cosine. So you could think of a gust going this way, and then back this way, and then going this way. Maybe a gust of wind isn't the right analogy. Sometimes you might see periodic forcing like looking at a flu epidemic. And what happens every winter time with the flu? I mean, don't they get like tons of cases, right? So there's seasonal forcing. So maybe the flu, you could talk about a population where an epidemic is dealing with the flu, but that population is going to be affected by the fact that it gets cold every, once a year. You get winter, and the flu takes a spike. So that's called seasonal forcing. That's an example of periodic forcing, but I didn't know how to make that a video, so I'm still using the wind analogy, if that's all right. So here we have a wind analogy on the underdamped case. And you'll see the wind go back and forth and back and forth. And that's going to affect the movement of the spring.
And underdamped is with just a little bit of friction?
Correct. That's right on. So a little bit of friction. Notice that we would expect if it's underdamped, we would expect things to settle down. Well, what keeps this thing oscillating? Well, it's the wind, right? The driving, the forcing is making this thing continue to oscillate. So there still is some loss of friction, but because the wind keeps blowing it, things can potentially keep oscillating back and forth, back and forth. Some interesting behaviors happen if the forcing frequency is of some particular values. Maybe you've heard of this phenomenon called beats. I heard of it first in the high school band because I was a band stud. To get that right. And we would have to tune our instruments, right? We'd have to make our instrument level with the tuner. Anybody have that experience? Maybe? Maybe not? Okay. And if you were close to the actual frequency, but not right on it, you'd hear wah, 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 wah. That behavior is what we mean by beats. And you'll get to see that in this video. Again, it's wind, just because that's the best. That's all I got for you. But if that wind is at a particular frequency, you'll see this phenomenon called beats, which is in the upper right part of your screen. Beats is what happens when you've got fast oscillations and slow, like a wave packet. Okay, so you have these slower oscillations right here. You'll see that pattern. And then fast oscillations right here, which make up the frequency that you hear. But the wah, wah, wah sound is this wave packet. So that's pretty interesting. That happens when you're forcing your mass spring system at some specific frequencies. And then the last one I'd like to show you before we go to the next slide is what happens when things resonate. Because resonance is a really interesting phenomenon where your wind is at just the right frequency that makes your spring grow in amplitude more and more and more. What do you think is going to happen here if this continues?
That thing's going to hit the wall.
It's going to hit the wall, exactly, or it's going to break, or like something bad is going to happen. It'll hit a threshold where the amplitude over here, I guess I should point at, gets so high that the threshold for the structural stability of the spring cannot withstand it. It'll break. Your bridge breaks. Your vase glass breaks if you sing at the right frequency. That's resonance. Your dryer or washer breaks. So sometimes we don't like resonance. In the band, we do like resonance. Yeah? You want to resonate your instrument with the right frequency, but sometimes in engineering we don't like resonance because stuff breaks. Maybe it's a drilling process, and if your drill is resonating, then it can break, and those are expensive things. All right, so I showed you guys what forcing was. The good news here is, even when you add forcing here, mathematically, we can find the solution if it's a linear case. We just add the homogeneous solution to the particular, we move on, everybody's a happy camper. Yay, so you guys like linear oscillators. It's good, right? It's good. Yeah, good stuff. Well, here's the problem. What if the differential equation is not linear? Oh, man. Well, it's not so simple. So here's some examples. You may have heard of the van der Pol oscillator, perhaps. Okay, well, that's a very commonly used example. The van der Pol oscillator has got applications. I couldn't even list them all, but here's a few. It's a very interesting oscillator. If you want to see what the van der Pol looks like under forcing, then you're like, okay, what's going on? If you periodically force the van der Pol oscillator, then all sorts of fun things can happen. This is a highly nonlinear oscillator. I tried to show you guys the nonlinearity in the equation. Maybe you spotted it. I highlighted it by color. I wonder if anybody caught where exactly is the nonlinearity. Do you see it? X squared, and it's really, you got x squared times x prime. The fact that there's that term in the equation makes e to the x not work. All right? E to the x is the solution basically for our linear cases, but these solutions are not known exactly. We are left to approximate them. The Rayleigh equation is another popular one, which shows up in the literature at times and is widely studied. The Duffing equation comes up in discussions of chaos, magnetism, and the nonlinear pendulum, and so on. I could show you, all sorts of different kinds of difficulties, but the key difficulty is right here. It's the nonlinearity, the thing that when you take a dependent variable, which in our case, what's the dependent variable? X, and you make it a nonlinear function, x squared, x cubed, sine of x, those sorts of things. I'm less worried about t. I don't know if y'all caught this, but you're like, wait a second, all right, cosine of omega t is not a linear function. You are correct, but there's no x's in it, right? It's the forcing. It's all a function of time. So I'm okay if I've got functions of time that are nonlinear, like cosines, sines, logarithms, e to the x's. Those aren't a terrible problem. I could still use the theory that we've discussed so far. I'm more worried about if my dependent variable is nonlinear. That's what we mean by nonlinear equation, and that's what makes it difficult to understand. This is a model, a Leinart equation. The nonlinearity is an x times x prime term, which makes this pretty difficult. And this shows up in coupled lasers, epidemics, and some other things. I've done a good bit of experience on this one, which is why I kind of closed this subsection with it, and I'll talk more about it when I get to some of the methods. So let's move right on to, nonlinear methods here. How are we supposed to solve nonlinear differential equations? Well, when in doubt, we pray. All right? Well, yes, that can be useful. I highly encourage prayer without ceasing. I imagine I'm in good company to say that. But I also would encourage graduate school. And we can learn some other sorts of techniques. Here's one of them, the method of multiple scales. I'll show you what's going on here. A fairly old method, 1843, 1847, You got all sorts of dates that are, 150, 200 years ago or so. And what's interesting, though, you see the word Neptune up there? They discovered Neptune in a pretty interesting way in 1947. He was actually studying the planets and was like, whoa, we don't have all the planets. Mathematically, there should be a planet right here. They didn't know it, but he predicted it based on mathematical equations, and then it was sometime later they were like, he's right. It's right there. There's a planet there. It's Neptune. That's how they discovered Neptune. It was predicted before it was observed. It's pretty crazy, right? And he was using some of these techniques. Rudimentary versions of them, but he was using them, and that impresses me. That kind of rocks my world that could happen. But here's the idea. We have two, maybe a nonlinear oscillator has two sorts of primary behaviors. Maybe it has sort of a slowly decaying amplitude, but some rather rapid oscillations. So if those sorts of qualitative behaviors need to be understood, then what we can do is separate your usual time variable into two time variables. Call one of them a fast time, little t, maybe the other one a slow time, and call it capital T, and we'll quantify it maybe by epsilon t, where epsilon throughout this paper and in many other contexts means a very small parameter. If it helps, imagine epsilon to be like 0.1 or 0.01, something that's tiny but still positive, okay? And so you got, time scales. Seconds versus years. Make sense? You have two different times. Over the case of a year, maybe this qualitatively long time scale stuff happens, but per second, these other sorts of behaviors happen. That's the idea behind method of multiple scales, and you can expand the solution that you want x as a series in epsilon in both independent variables, and you end up collecting like powers of epsilon and eliminate resonant terms. I'm really condensing a big idea into like a bullet, and that's not easy to do, but we did. I can show you a couple examples of this, or one example. This is a pretty tricky nonlinear equation to solve. It doesn't have a solution that I know of, but we can approximate it using method of multiple scales, because you see some two different sorts of behavior. What you're looking at here, is the red and the blue is an interaction between solving it numerically with the computer versus solving it with that equation you see up there. And that's not the exact solution. It's just an approximation. Can you all see a difference between the two? The difference is pretty clear over here, right? But it's especially, for small epsilon, this method works very well. There's almost no difference between the computer simulation and the analytical solution. So as epsilon gets really small, these approximations work very well, which is what they're designed for. That's method of multiple scales. Poincare-Linstead method, also fairly old, been around for a while. I don't know if I'll get to say much more about this, but I'd like to kind of keep cruising. I'm making some good pace. But I will point this out. Do you see that word right there? Anybody in Calculus 2 or Calculus 3?
Yeah.
Woo! Is this your favorite thing ever?
No. Sure.
All right. Series are really important in the applied sciences. Really important. And whether they converge or not is a big idea that you first get to touch on in Calculus 2. So you'll see series expansions show up over and over. One more example, another method. So we have multiple scales. We've got Poincare-Linstead. Matched asymptotics is perhaps interesting to some of you because we've got a whole aeronautical science division here, right? Isn't that sort of some of the history of LeTourneau? And there's something called the no-slip condition for an airfoil, where fluid typically flows. We think of it flowing right past a plate or a wing, but the truth is if you could zoom in really close to that plate, it's not moving when you're on it, right? And that's a no-slip condition. And so that creates what's called a boundary layer, where the behavior when you're close to the plate is significantly different than the behavior of the fluid or air away from the plate. And it's only in that tiny little layer where things are different, and that's called a boundary layer. And mathematically, we can deal with that. It's usually a highly nonlinear problem, and we can approximate those sorts of solutions with a method called matched asymptotics. Here's one quick example where you can see I've got a nonlinear differential equation here. It's a boundary value problem where I need the solution to hit at this spot, and I need the solution to hit at this spot. But what's going to happen to the solution for various values of epsilon? And you see as epsilon gets smaller and smaller and smaller, the approximation is doing really well. And in fact, I can see the boundary layer basically right here. Imagine this like a wall, and the distance, I'd have to kind of zoom in, but left to right, that distance from here to that peak is really small, right? So that this thin thing right here is what we would call the boundary layer, where the behavior is different than in the large, away from the wall, things operate pretty smoothly. It's a nice line, but then near the boundary, it's like, phew. And that happens because, in this case, it happens because the epsilon is on the highest order derivative. But I could go on and on about that. But that's particularly interesting in airfoil theory and aerodynamics, I think. But that's not even it. The method I'm going to spend the rest of my time talking about, my last 10 or 12 minutes or so, is another method, a new sort of attack at this problem. How can we deal with nonlinear problems? All those ones I mentioned so far are relatively old. They're great, and we still use them. We teach them in grad school, in applied math departments and so forth. It's how I learned it, was in grad school. But are there some advantages to some newer methods, and what can we learn from them? And I'm going to talk a little bit about the homotopy analysis method. I know some of you already have Thanksgiving in minds, and you're looking at this word ham, and you're like, oh man, is he about to talk about food? Or no, that's an unfortunate acronym for the homotopy analysis method. So if I slip up and say the ham, I'm not referencing the wonderful feast that is headed our way over the break. I hope you get a break, but in any case, I'll leave that to the powers that be. Some quick examples. A homotopy is a continuous function that basically deforms something that's maybe well behaved to something that's maybe more nonlinear. If you could sort of get that to happen, and I don't know if this analogy helps, but this is the way that I kind of sort of think about it as a concept. This is not frowny face. This is how I think about it. That's all right. Okay. I'm sure I was bound to have one broken link, right? But hopefully the others are not like that. That the idea would be in a multivariable calculus class, there are times when you use change of variables equations that get you from things that are nice and neat boxes to things that are distorted, sort of weird polygons, okay, four-sided shapes and stuff. And that transition, that change of variables, can be an example of a homotopy. It's a continuous function that maps some sort of shape to another shape in a continuous manner. Well, we're going to try to use that to solve some nonlinear problems. And there was a book that came out in 2004 that was sort of the motivator for me as I undertook this project. Maybe about 2 years ago, I was kind of started on this. Had never even heard of the ham a couple years ago, but now it's sort of one of the current modes of research that I'm on. But so I guess I pointed that out just because I'm not saying like 1850, right? So on the scale of math, this is pretty recent. A quick example for using homotopy analysis method, there's a skydiver example that the textbook goes through, and it's like, okay, if I had the velocity is now my dependent variable of a skydiver, then the derivative of velocity is what? Acceleration. So this is still Newton's second law of motion, by the way. It's just the fact that you've got acceleration term here, and you've got your friction force proportional to the square of your velocity instead of proportional to the, the dependent variable itself. So that's a little different model. But if this is the model that you're dealing with, then you end up getting the hyperbolic tangent function as the solution. And let's cross our fingers and hope the link's not broken. I'm going to use the second link. I did, you know what? This is from a previous presentation, and I copied and pasted the slides, and you live and learn. Maybe I created the link when I was still logged in. I could hypothesize for, I don't know what happened. But here's the basic idea. We'll wing it. The basic idea is we are going to still expand the velocity as a series in a different way, and maybe we want to expand it as a certain form of function. So there's times you can use the ham to expand it as polynomials, which is not a great choice, because what happens at the ends of polynomials? You guys know what happens at the far left and far right of a polynomial? Right? They blow up. And that's not going to happen for the hyperbolic tangent function. That thing kind of hits a horizontal asymptote. Exponentials are better ideas, because decaying exponentials at least have horizontal asymptotes as time moves forward. So expanding the solution as exponentials works out pretty well. But I'll leave that there. This method, the ham, was used on van der Poel's equation in 2009 in a paper that I read. It did pretty good. I mean, you can see the same shape that you saw earlier for van der Poel, and Lopez and some others worked out the amplitude there, the limit cycle that's part of that. Some others more recently used the homotopy analysis method to approximate amplitude to Rayleigh's equation, which I showed you guys earlier. And it does a pretty good job of mapping that out. And some of what I'm working on right now is applying it to the Leinart equation, which was this up at the top. That was useful in lasers back in the 90s, and a model of epidemics in 2009, and then a paper in 2011. It was applied to microparasites, which apparently I like. I like parasites. I'll keep milking that one. And what we ended up finding was I used the ham to approximate the frequency of those oscillations. For this particular model, it turns out to be a conservative model, which means that you can actually derive a potential that is a constant function. It does not gain or lose energy. That's one benefit. Even though it's nonlinear, it's conservative. That's nice when we have a conservative model. So what we can do then is approximate what its frequency is, because its frequency is not easy to predict. How often is it going to make that cycle? And as funny as that shape was, I'm going to see if I can. That was this last case right here. So this is a pretty funny shape. These are the solutions you end up seeing for this equation. You have high pulse right here, very sharp peak, and then sort of a lag time on the other variable x. Oh, I didn't explain that, but you guys see these y's here? The y is the velocity. Okay, that's the derivative of x. And just in case you're curious about that. So these funny shapes here, we're trying to predict how quickly it's going to run through these oscillations. So that's right here. Unfortunately, we need kind of a computer algebra system. Because, I mean, not unfortunately, maybe that's a good thing. It's good to have computer algebra systems. Every little bit of coding experience you guys have, I would highly recommend you just soak that up. Some of us really hate coding and programming. Some of us thrive and love it. But we are in a day and age where coding is really, really important, no matter what the application is. I'm not a computer scientist, but encoding and using computers is a really, really, really helpful thing.
What does your h-bar represent?
Great question. It is the auxiliary parameter that is, one of the benefits of the ham is it does not require epsilon be small, so it works for systems that aren't that don't have to have that epsilon small. All of our series for multiple scales and matched asymptotics, they require an epsilon be small, and you expanded your series in epsilon. Well, the ham doesn't require that, and the way that it sort of gets in the back door with that idea is throwing in an auxiliary parameter h bar. It's not the, what is it, Planck's? It's not Planck's constant, so that was probably your, so, sorry for the similar notation, it's not Planck's constant. But it's sort of a way that you can still expand the series without requiring epsilon be small. That's my short answer there. But you see that this is pretty lengthy and complicated, and you need a computer to kind of work some of this stuff out for us. But the approximation worked out pretty well. this is a picture of the approximation of frequency for this model, where you've got the pink curve here. Y'all see that kind of dying off? That was using Poincare-Linstead method, which has its benefits, versus the red curve was me using the homotopy analysis method, and the blue is solving it numerically with the computer, which means it is approximating frequency, but it's not able to give you an expression for like, here's the frequency. It's just like, you know, floating points. Like here's the number. Who knows how it became that number, right? But the ham actually gives you expressions for how it depends on the parameters of the model. And it does pretty well as far as approximate, at least much better than the Poincare-Linstead method, which is really only designed for weakly nonlinear oscillators instead of...
When you say numerical or computer, you mean something like a second order Runge-Kutta?
Yeah,
Numerical.
that's a fine example. I use MATLAB most of the time, but it has a built-in fourth order Runge-Kutta method that I use, ODE 45, I think. But there's pick your favorite ODE solver, right? That is out there, and then use it appropriately. That's what's generating these frequencies. Interesting point I will say is that you have to be a little clever with this model, because the picture here, it turns out there's a wall down here that it cannot pass at the bottom. It can't pass that. And numerically, as things step along the way, right? I don't know, anybody taken, well, I don't know, numerical methods? Do you have a numerical methods course, I would imagine? And you have to step with the Euler method, maybe? If you step in the Euler method, you cross that wall, then the solution goes, and then it goes off to infinity. And it basically stepped across a line it wasn't supposed to step across. And you have to be pretty clever about keeping it on the right side of the wall by a change of variables. But there's some other little tricks there you can use to make sure it's not spitting out crazy results. Don't just plug in a computer, read the picture, and go, here's my absolute answer, right? You always got to make sure it's a reasonable answer. And that takes some critical thinking. But so here we go. This is using Poincare-Linstead is the dotted line, and the ham is the solid line. I'm sorry, numerical is the solid line, and it's failing because the nonlinearity is pretty strong. So this is not a great picture. It's not approximating it very well, as opposed to the ham approximates it pretty well. So this is a very strong nonlinearity, and yet the ham's doing a fine job. So kind of put that in a paper, submitted it, waiting to hear back. Let me close out the several perturbation methods or perturbative methods that we mentioned, multiple scales, Poincare, matched asymptotics, WKB we didn't get to talk too much about. I've got a slide in the appendix if there's time. But the homotopy analysis method is a little bit newer. I've got some slides in the appendix with more details on it. But for now, its benefits are this. It doesn't require epsilon b small. You can, for strongly nonlinear oscillators, the ham can still sort of work, you might say. But the limitation is you've got to carefully choose the auxiliary parameter h, which is not Planck's constant, and you have to carefully choose the linear operator that's associated with that problem. And so there's some more details there, but it is a little, it's rather exciting to kind of think through that. Maybe your takeaway as a student might be the knowledge that series are pretty important. Hope you kind of take that stuff seriously. You got all your convergence tests that you got to think through and so forth. What I'm working on now is other uses of the ham, maybe incorporating a delay. I've done some research in the past delays. I'm wondering if I can combine the two ideas. And I'd maybe want to compare it to Kuzmak's approach. Kuzmak's approach is a little more well-suited than Poincare-Linstead as far as comparing it to the ham. I kind of set up an unfair fight. The ham was going to do better, and the Poincare was not going to do as good. And I knew that going into it. That doesn't sound fair, but maybe I could take a different method there. And then here's a paper that was in the 90s, and then as recent as 2015, some mathematicians were talking through the renormalization group method. So I'm looking into some of those things, still learning. I'm very grateful to LeTourneau for the invitation to SFA, where I work, and providing this this opportunity. I will take a moment to use a shameless plug and tell you guys we have a graduate program. We have a master's degree program. And so you may be hearing from your faculty here or from others at other institutions that encourage you to go to grad school. And a lot of you are going to be well suited for that. Nacogdoches isn't but a hop, skip, and a jump away. I made it in good time this morning. But we have a good mathematics master's degree program and statistics master's degree program. If you are interested, I'd love for you guys to come down and you can ask me questions about it, and I could give you some details. I do have a few things that are free or a giveaway. Dr. DeBoer was kind enough to actually give me some warm water to demonstrate. Oh, it's cooled off. I should have done it at the beginning. You live and learn. Did y'all? Some of you were here early, right? Did y'all see it turn pink? Okay, we don't have to tell everybody else. You were witnesses. But if you warm this thing up, it's just a ruler. If you warm it up, it turns pink. It's kind of fun. And then you cool it off, it turns purple. So y'all can come and grab free stuff if you want on your way out. Stick around for questions. You may have questions right now. Is there time for questions?
Time for questions.
All right, thank you for your attention. I'm done.
Well, let's have some questions for Dr. Mitchell here. Go ahead and take them if you wish.
So, my ultimate question is, I know you kind of alluded it at the beginning, but why would this be important in everyday life? Like, what would this translate to that would have some, I don't know how to say it without, like, saying that this is not important, but I'm saying, how does this affect my daily life?
The best example that jumps to mind is the one where people could lose their lives, I suppose. When you build a building, you want it to withstand certain winds and structurals. Somebody shouted out bridge earlier, right? That's an oscillator. But yeah, this is everyday life. So engineers need to make structures that have some damping and have some give that is not strong enough to break, but weak enough to allow it to oscillate. Because it's going to oscillate whether you want it to or not.
So how would the ham research, as delicious as it sounds, apply to mass dampers and the like?
It would apply in the sense that the equations that govern the structure of a building are highly nonlinear, make them impossible to solve perfectly, and so we are left to approximate things. And so this is just another method. I'm not even saying it's the most perfect method because I'm well aware of its limitations, but it is a way to approximate solutions that wasn't around 20 years ago.
And from these solutions of the oscillation, you can therefore correctly and accurately engineer a solution that will fix the oscillator to the best effect.
That's the goal. Yeah, you've got, anytime you're modeling something, there's kind of a give and take between efficiency and accuracy. And this is across the board in the sciences, right? You want an accurate model, but you need it to be efficiently computed. And you could have it as accurate as you wanted, but it's so complicated it can't efficiently compute it with today's computers. Or you could have it really efficient and it's not accurate. So you want models, approximations, and things that kind of find the best of both philosophies.
Would you categorize ham as being an analytical method or a numerical method?
I'd say analytical.
Okay.
So I brought up the computing because it's not computing it numerically with floating points and it's a computer algebra system. So I had to it's an iterative process. You're still expanding the solution by a series, and you're only taking the first 4, 5, 6 terms of the series that are your approximation. So Sage, Maple, Mathematica are some popular computer algebra systems people use.
Is the algebra so difficult that you'd only really do it using some computer support?
Yes.
Is
The
it not
first-
something you would do by hand?
The first term you could probably do by hand, and I've done some of these problems just to kind of make sure my program's working right. You got to do the first or second term of the series to be like, is it giving me what it ought to? But then it's like, well, I'm not doing this again for the third iteration. And then you kind of rely on the computer. And then you test it with what a numerical algorithm would do, and if there's some agreement, then there's a bit of a sanity check. Yeah.
Other questions? Okay, I want to remind you we'll be in the
Oh.
Joyce room. Oh, question?
I was going to ask, I know that there are some headphones now that have sound cancellation. Can this apply to aircraft in certain key frequencies instead of just vibrations?
Short answer, I don't know. But I would imagine so.
Okay. All right, so just a reminder, we'll be in the Joyce room if you want to join us for lunch.
Yeah.
Let's thank our speaker.
Thank you, guys. Come get some free stuff. If you want, take one on your way out. I've got plenty.